Over the centuries, scientists have unraveled countless mysteries of the cosmos through careful observation, experimentation, and patience. Yet one of the most enduring questions in astronomy remains surprisingly close to home. We have never actually witnessed how a solar system like our own is born. Our current understanding of planetary formation is largely built on inference, extrapolated from meteorites that fell to Earth and detailed studies of the neighboring planets orbiting our Sun. And in many respects, astronomers believe this picture is broadly correct. The models we've constructed are internally consistent, and on the surface they seem to explain what we observe. Still, critical pieces of the story have remained frustratingly out of reach. Exactly how, when, and where planets first take shape has long been one of the biggest unanswered questions in planetary science. But that is now beginning to change. Earlier this year, the James Webb Space Telescope identified a newborn star deeply embedded within a dense cocoon of gas and dust, and within that swirling cloud, planets are actively forming. For the first time, humanity is able to observe the very earliest stages of planetary birth. This discovery doesn't just help us complete a long-standing puzzle. It may also reveal how our own solar system came into existence, including the processes that eventually made life on Earth possible. Join me as we uncover the secrets of HOPS 315, explore what its future planetary system may look like, and examine how this remarkable observation is reshaping our understanding of planet formation across the universe. Considering that we live on a planet, have sent spacecraft to 7 others in our own solar system, and have discovered more than 6,000 planets beyond it, you might expect astronomers to have a clear, complete picture of how planets are formed. The reality, however, is far more complicated. Much of what we know today comes from the chemical analysis of ancient meteorites that have fallen to Earth, combined with detailed observations of the planets as they exist in their mature present-day states. Everything else has relied heavily on theoretical models and computer simulations, and there's a reason for that. The earliest phases of star and planet formation are notoriously difficult to observe. The process begins inside enormous molecular clouds, vast regions filled with gas and microscopic dust particles. As these particles move, they generate thermal pressure, pushing outward against the cloud itself. At the same time, gravity is always at work. Every particle pulls on every other, drawing the cloud inward. For millions of years, these opposing forces, outward pressure and inward gravity, can remain in near-perfect balance, keeping the nebula stable and unchanged. But that balance is fragile. A nearby cosmic disturbance, such as shock waves from a supernova explosion, can suddenly disrupt this equilibrium. If gravity begins pulling the gas inward, faster than thermal pressure can resist, a runaway process is triggered. The cloud collapses under its own weight, and a star is born. The dust and gas from the outer reaches of the cloud begin to rain inward. As this material compresses, the core grows denser and hotter, spinning faster and faster, much like a figure skater pulling their arms close to spin more swiftly. A pronounced heat gradient develops, with temperatures soaring above 1000 K within 1 astronomical unit, the distance between Earth and the Sun, and gradually cooling to around 400 K at 5 astronomical units. Over the next 100,000 years, most of the mass congregates at the center of the cloud, eventually forming a protostar, while the remaining material spreads outward, creating a protoplanetary disk, a swirling, dusty womb encircling the stellar embryo. It is this dense shroud of gas and dust that makes observing stellar formation so challenging. Even our most advanced telescopes struggle to peer through it. Yet, as technology has advanced over the decades, astronomers have begun catching tantalizing glimpses. In 2013, a team led by Amelia Stutz turned the Herschel Space Telescope toward the Orion Molecular Cloud Complex, the largest nearby site of star formation. This initiative, known as the Herschel-Orion Protostar Survey, or HOPS, focused on the Messier 78 nebula. HOPS revealed 15 previously unseen protostars, with masses ranging from 1/5 to twice that of the Sun. These stars had remained hidden because their gas envelopes are extremely cold, heated to just 20 degrees above absolute zero, with the nascent stars buried deep within. This frigid state indicates that these stars had not yet begun to warm their surroundings, making them some of the youngest protostars ever observed. Stutz and her team finally had a benchmark to test and refine existing models. How do planets form? But the story doesn't end with the birth of a star. The formation of planets remains an equally profound mystery. Simulations suggest that within the dense mid-plane of the protoplanetary disk, dust and gas particles begin to coalesce. Microscopic grains collide and stick together, forming larger aggregates over millions of years. These solid clumps gradually grow into planetesimals, the primordial building blocks of planets, spanning several kilometers across. Through continued collisions and gravitational interactions, these planetesimals can eventually merge to form planets. The challenge is that most of this process has never been observed directly. Astronomers have discovered young planets. One, for example, has 4 times the mass of Jupiter and is less than 5 million years old. Even in this case, the host star itself is only about 2 million years old. By the time we spot these planets, they are already fully formed, leaving a gap of hundreds of thousands, if not millions, of years of planetary evolution unseen. Until now, HOPS 315, located 1,300 light-years away in the Orion Nebula, a baby solar system is in the making, and we are witnessing it through the lens of the James Webb Space Telescope. This is HOPS 315, a star younger than 150,000 years with a mass of 0.6 solar masses. It is still growing, feeding on the surrounding envelope of dust and gas that cloaks it in a cloudy veil. Remarkably, astronomers identified a gap in the clouds and managed to capture an image. What they saw was extraordinary. Infrared spectra from Webb revealed the presence of both warm silicon monoxide gas and tiny crystalline silicates near the young star. We were witnessing the moment gas begins to condense into solid material for the first time. This is monumental because, as a protoplanetary disk cools, compounds crystallize in a predictable order based on their condensation temperatures, a process known as the condensation sequence. By understanding chemistry and studying primordial asteroids, natural time capsules from the early solar system, scientists can infer this sequence. The oldest condensates trapped in these asteroids are calcium-aluminum inclusions, or CIIs, along with crystalline silicate materials. Observing both silicon monoxide gas and crystalline silicates around HOPS 315 demonstrates that this system is at the very beginning of its formation. In essence, we are witnessing the first stage of planet formation, unfolding in real time, a glimpse of planetary birth as it happens for the very first time. This discovery marked a major breakthrough. Eager to explore further, Professors Melissa McClure and Merrill Van Hofber earned the Atacama Large Millimeter Sub-Millimeter Array Telescope ALMA BRA award this infant star. AB Planetspur. Heil JWST revealed the warm inner regions of a young planetary system through infrared light bar. LMA specializes in observing the much colder material, gas that emit millimeter and sub-millimeter wavelengths of electromagnetic radiation. His allows astronomers to map both the chemical composition and the structure of molecular clouds. What's particularly fascinating is that this activity occurs roughly in the same region around HOPS 315 BR. Similar materials form around our Sun. Fully understand the implications. BRI strongly suggests that the earliest building blocks of planets, Y, develop in a similar way across multiple young systems. Though silicates were detected, the outflow jet observed by the team had an unexpectedly low silicon content, very element crucial for forming silicates and ultimately planets. Lie about 2% of the silicon McClure anticipated appeared, relative to the amount of carbon. McClure notes that may be a hint that planetesimals are already forming there, in a way similar to what must have occurred in our own solar system. His finding is remarkable given the system's youth. Are now able to timestamp the beginnings of planetary formation less than 150,000 years after a star begins to form. An insight that is challenging long-standing models. Previously, astronomers believed that gas condensation only began The star had stopped growing, and the remaining debris disk was relatively calm. For the past decade, however, mounting evidence from several young protostars suggested that planet formation actually begins much earlier. Earlier disks were often not well characterized. OPS 315 has confirmed those suspicions and taken the discovery one step further. A major question from the nebula hypothesis remains, How do millimeter-sized chondrules grow into kilometer-scale rocks? Mole particles resist sticking together. Sized objects risk spiraling into the star within roughly 100 years due to gas drag. A compelling idea is that dust collapses in pockets of gravitational instability directly, a solid rock emerging from a storm of sand. Why repeatedly observing changes in the gas-to-solid ratio in HOPS 315 bar, scientists can trace the speed at which solids grow, identify factors that limit their coalescence, and understand how this shapes planet development. Perhaps most strikingly, the HOPS 315 system is one of the best we know to actually probe some of the processes that occurred in our own solar system. By comparing HOPS 315's dust chemistry with meteorites on Earth, astronomers can see whether the same condensation sequences and elemental distributions that formed our planets are replicated elsewhere in the universe. For the first time, we can test our models against reality. What's next for HOPS 315? As is always the case in science, each discovery raises new questions. What comes next for HOPS 315? How many planets will form around this star? Will the system mirror our own, with small rocky planets in the inner regions and icy gas giants in the outer reaches? The answers will come with continued observation, but one thing is clear: HOPS 315 is providing a front-row seat to the birth of an entirely new planetary system. The condensation sequence within a protoplanetary disk has a direct influence on the types of planets that form and where they take shape. This allows astronomers to make educated predictions about a system's architecture. Because the early disk is not uniform in temperature, different compounds condense at different locations. One key feature in this process is the snow line, the distance from the star beyond which temperatures are low enough for ices to form in our early solar system. This line sat around 2.7 astronomical units from the Sun. Beyond the snow line, ice and dust accumulate, gradually growing into massive planetary cores. The colder environment also slows down gas movement, allowing these frozen cores to capture surrounding hydrogen and helium. Once enough gas is accreted, a gas giant emerges. This process occurs surprisingly quickly. Astronomers believe it took as little as 10 million years for Jupiter and Saturn to form. Inside the snow line, however, ice and volatile compounds are completely vaporized. Only materials with extremely high melting points, iron, nickel, aluminum, and rocky silicates, endure. By this stage, most of the disk's gas has already been captured by the growing star or outer gas giants, leaving little to fuel the formation of inner planets. The result is smaller, rocky worlds like Mercury, Venus, Earth, and Mars in our own inner solar system. For HOPS 315, we don't yet know how many planets will eventually form, but astronomers anticipate a similar configuration, with rocky planets closer to the star and gas giants in the colder outer regions. That said, planetary migration and the potential presence of hot Jupiters cannot yet be ruled out. Given that the earliest stages of planet formation in HOPS 315 are occurring roughly at the location of what would become an asteroid belt, one question arises: will this star have one? In our own solar system, the asteroid belt sits between 2.2 and 3.2 astronomical units, and asteroid B. LTs are not unique to us. In 2001, astronomers discovered the first belt beyond our solar system, 70 light-years away around Zeta Leporis, a star roughly 1,000 times older than HOPS 315. Whether an asteroid belt forms around HOPS 315 depends on several factors. Our own belt exists because of Jupiter. Initially, the region between Mars and Jupiter was filled with dust and planetesimals, enough material to form another planet, but once Jupiter formed and grew massive, its gravitational influence disrupted the surrounding region. Orbital resonances prevented planetesimals from coalescing, leaving behind a collection of primordial debris, the asteroid belt we know today. For HOPS 315, a similar belt could develop if a massive planet forms and creates gravitational disturbances like Jupiter did. If no sufficiently large planet emerges, the system might instead host an intermediate world near the snowline, a configuration our own solar system never experienced. HOPS 315 is, in many ways, a portal to our own past. Studying it is like peering at the solar system 4.6 billion years ago, when Earth itself was little more than a cloud of dust and gas. At the same time, Its discovery raises profound questions. How common are systems like ours? Does planet formation always initiate around 2.2 astronomical units? And how rapidly does a protoplanetary disk evolve from microscopic dust to fully formed planetesimals? To answer these questions, astronomers are expanding their searches for other very young stars, hoping to identify systems similar to HOPS 315. If multiple examples are found, we may have discovered a true protoplanetary gold mine, an unparalleled dataset for understanding the origins of planets and planetary systems. Regardless of what future observations reveal, one fact remains certain: our own planet and solar system began as a swirling cloud of dust, and billions of years from now all of it will return to dust once more. Perhaps then, while we exist in the brief window between birth and decay, we should make the most of our fleeting time in the cosmos.